Hello there, and welcome to the Sleepy Science Channel. Tonight, we'll be drifting into the vastness of space, far beyond the calm orbit of our Earth. To meet a star so enormous, it would stretch well beyond the edges of our solar system. A star swollen with heat and time, shining at the very limit of what a star can be, and slowly, silently, coming to the end of its life. Out there, in the deep dark between constellations, some stars don't just glow, they loom. Their atmospheres reach across billions of kilometers, wrapping themselves in shimmering layers of gas, trembling at the edge of collapse. But even they must one day vanish. What happens when a star becomes too large to live? How do we measure something so vast it can barely hold itself together? And what secrets are written in the fading breath of a dying giant? We'll explore all of that, quietly, patiently, as we follow this enormous star from its slow beginnings to its final, spectacular fall. If you enjoy these gentle wanders through the cosmos, we'd love for you to like and subscribe to the channel, and maybe even leave a comment of what you'd like to watch next. But for now, let's begin. Some stars are so large, so swollen with mass and heat, that they seem to defy reason. They burn with a deep red glow, vast and bloated, their outer layers trembling at the edge of gravity's grasp. These are the hypergiants, the most voluminous stars we've ever observed. Among them are names like Stephenson 218, Ui Scuti, and VY Canis Majoris, stars so immense that our entire solar system could fit comfortably inside their envelopes, with room to spare. These are not stars we see with the naked eye. They live far beyond the familiar constellations, hidden behind dust clouds or buried deep within galactic clusters. But with the help of infrared telescopes and spectral analysis, astronomers have brought their existence into view. Stephenson 218, for example, is a red supergiant located near the constellation Scutum. Discovered in a dense star cluster of similar giants, it may be the largest known star by radius. Though it's hard to pin down exact measurements, estimates suggest it could be over 2,000 times wider than the Sun. Then there's Ui Scuti, once considered the record holder, located roughly 9,500 light-years from Earth. Its radius is also estimated to be well over 1,000 times that of the Sun. And VY Canis Majoris, an older giant surrounded by drifting dust, offers a glimpse at what happens as stars this size begin to decay. These stars are not necessarily the most massive. They don't all weigh more than other stars, but by volume, by sheer physical extension, they are the true giants of the cosmos. But what does it mean to be 2,000 times larger than the Sun? These comparisons can be hard to picture. The Sun, after all, is already enormous. More than 100 Earths could line up across its diameter. Yet these hypergiants would dwarf it to invisibility. If we replaced the Sun with Stephenson 218, its surface would reach out beyond the orbit of Saturn, a blazing red globe that would swallow every planet from Mercury to Jupiter whole. Even Ui Scuti, slightly smaller, would still engulf the entire inner solar system, reaching past Mars and halfway to the gas giants. Imagine looking up at a sky where the horizon blurs into a wall of glowing rust-red gas. From Earth's current position, we wouldn't see a sky at all. Just atmosphere pouring off a distant dying titan. The scale isn't just vast, it's alien. These stars don't have surfaces in the way planets do. Their outer layers are so diffuse, so stretched by heat and light pressure, that the boundary between star and space becomes a kind of twilight zone. The density near the outer edge can be thinner than air, yet it's still part of the star. You could drift for hours, maybe days, through the upper atmosphere of a hypergiant, before reaching anything resembling its inner structure. And all that time, you'd be surrounded by plasma, ionized gas glowing with light from deeper below. Even though the human mind struggles to grasp such scales, astronomers have developed ways to measure them. By analyzing the light curves, infrared emissions, and spectral absorption features of these distant objects, we can estimate how large they must be to produce the kind of luminosity we observe. These calculations are always evolving, margins of error are large, and dust clouds can obscure part of the truth, but the general picture is consistent. Some stars really are this large. They live briefly, radiate furiously, and eventually dissolve into collapse. And as we begin to explore how these giants came to be and why they're already dying, it's worth remembering that scale alone doesn't ensure survival. In fact, for stars like these, being large is often the beginning of the end. When astronomers measure the size of a star, especially one located thousands of light years away, they are not measuring anything directly. There are no cosmic rulers and no way to see these distant stars as disks with clearly defined edges, at least not with conventional telescopes. Instead, scientists rely on a combination of brightness, temperature, and distance. By studying how much energy a star emits across visible, infrared, and sometimes ultraviolet wavelengths, and comparing that to its distance from Earth, they can estimate its luminosity. Then, using basic physics, they calculate how large the star would have to be to produce that much light at its observed temperature. The result is a radius, not measured in kilometers, but in solar radii, or multiples of the sun's size. This method is far from simple. To estimate a star's radius accurately, astronomers must know its exact distance, which often comes from parallax measurements taken over months or years. They also need to account for interstellar dust, which can dim or scatter the light we see and cause a star to appear cooler or smaller than it truly is. Some stars, especially red hypergiants, also have extended atmospheres and variable surfaces, meaning their size is not fixed, but shifting over time. Even so, by analyzing their spectral lines and applying models of stellar structure, scientists can arrive at surprisingly consistent estimates. A star like Stephenson Toy-Team may never be outlined clearly on a photographic plate, but its light tells a story, and that story is written in scale. Even for astronomers, the resulting numbers can be difficult to internalize. A star 1,000 times the sun's radius doesn't just sound large, it bends the imagination. So let's try to make that scale more tangible. The sun's radius is about 700,000 kilometers. Multiply that by 1,000 and you reach 700 million kilometers, far enough to reach beyond the orbit of Jupiter. Now imagine placing such a star where the sun currently sits. Mercury, Venus, Earth, and Mars would all be incinerated and absorbed into its outer layers. Jupiter itself might orbit just inside its visible surface. The idea that such a thing could be real, not theoretical, but observable, is both humbling and astonishing. Imagine Earth's entire orbit, the full journey we make around the Sun in 1 year, tucked neatly within the gaseous limb of a supergiant star. We would not see sunrise or sunset. Instead, the sky would be a constant glow, rich with red and gold, the atmosphere pulsing gently with the tides of convection and radiation pressure. Day and night would vanish. The sun would not be a dot in the sky, but a horizon of burning clouds rising on every side. For a planet like ours, life would be impossible, but from a distance, the sight would be beyond beautiful. To make things more relatable, astronomers sometimes use analogies. If the sun were the size of a basketball, Wee Scuti would be a sphere nearly 60 meters across, the length of a passenger jet. If Earth were the size of a pea orbiting the basketball, it would sit far outside the jet-sized hypergeo, swallowed many times over. Or flip the metaphor, if Earth were the size of a marble and we placed it next to a star the size of a redwood forest, that would begin to approach the scale we're dealing with. These comparisons are imperfect, but they help us grasp the truly non-human proportions of these celestial giants. It's tempting to think of them as rare or isolated, but red supergiants and hypergiants exist throughout the Milky Way. Most of them are transient, massive stars that have reached a late stage of evolution. They do not stay this large for long. In fact, their immense size is part of their instability. The very forces that make them expand, radiation pressure, fusion output, internal turbulence, also lead them toward collapse. And soon, that collapse will come. Not all enormous stars are alike. When we speak of giants, we enter a spectrum, one that ranges from the modestly large to the truly extraordinary. At one end are the red supergiants, like Betelgeuse, a familiar point of red light in the shoulder of Orion. These are stars that began their lives several times more massive than the Sun and have now expanded dramatically in their old age. Red supergiants are common endpoints for stars between about 10 and 20 solar masses. They are cool on the outside, luminous from within, and often surrounded by drifting clouds of expelled gas. They mark a temporary phase, a swelling, trembling stage before collapse. But then, there are the hypergiants. These are not merely larger, they are fundamentally more unstable. A hypergiant is a star that has not only expanded to an enormous size, but also shows signs of severe atmospheric instability. Its outer layers are not held neatly in place, but pulse, flare, and shed mass in powerful outbursts. They often have spectral anomalies, strong stellar winds, or complex circumstellar environments. The distinction between supergiant and hypergiant isn't just about size, it's about behavior. A red supergiant may swell and dim gradually. A hypergiant might do so violently, shedding the equivalent of Earth's mass in gas every few years. In the sky, both types glow red and vast. But beneath the surface, their lives tell different stories. The sheer size of these stars is the result of a delicate and temporary balance. Inside the core, nuclear fusion pushes outward, a constant expansion driven by the heat of atoms colliding and fusing into heavier elements. But surrounding that core is the force of gravity, pulling inward with relentless pressure. In a stable star, these two forces are in equilibrium. But in a massive star nearing the end of its life, that balance becomes unstable. The star has burned through its hydrogen fuel and now fuses heavier and heavier elements in layered shells, like an onion. This creates complex pressure zones, causing the outer layers to expand far beyond their original bounds. As fusion continues into heavier elements, helium, carbon, oxygen, and beyond, the energy output becomes more extreme, but less efficient. The inner core contracts, heats up, and shifts to new fusion stages. The outer layers, meanwhile, balloon outward in response to the rising pressure. These outer zones become diffuse and tenuous, expanding into near-vacuum conditions that barely cling to the star's gravitational pull. That's why a hypergiant can grow so large, not because it's a solid object swelling like a balloon, but because its outer plasma is being lifted outward by immense radiation and thermal pressure. In these expanded states, the density of the star's outer envelope can be incredibly low. A cubic meter near the visible surface of a hypergiant might contain fewer particles than the air inside a room on Earth. Yet it still glows, still radiates, and still counts as part of the star. Light and heat pour outward from the deeper, denser core, but pass through these ghostly outer layers on their way into space. From afar, the star appears massive and luminous. Up close, it would feel like drifting through a fiery fog. The instability of these outer zones creates constant motion. The surface isn't smooth, it churns with convection currents, massive rising bubbles of hot gas moving from deep within. This can lead to temporary brightening or dimming of the star, depending on where those bubbles break the surface. Occasionally, the star will throw off parts of its atmosphere entirely, creating arcs or clouds of material that drift nearby, glowing in infrared. These motions are not accidents. They are the natural consequence of a system reaching its limit, of a star growing too large to hold itself together. And when that limit is reached, the star's story begins to change. No longer merely expanding, it begins to prepare for collapse. But that journey, from trembling giant to dying core, has only just begun. Every star, no matter how vast it becomes, begins its life as a cloud, in the quiet arms of spiral galaxies or the dense knots of stellar nurseries. There exist regions filled with cold molecular gas, mostly hydrogen, laced with traces of helium and heavier elements. These clouds can be immense, stretching across dozens or even hundreds of light years. But under the right conditions, gravity begins to pull the gas inward, causing it to clump, compress, and slowly collapse. Within these clouds, pockets form, denser regions called prestellar cores. And over time, if enough mass gathers, something remarkable begins to happen. The temperature rises. As the gas contracts, it heats. The atoms begin to collide more frequently, and the pressure at the center grows. Eventually, the core becomes hot and dense enough for hydrogen atoms to overcome their mutual repulsion and begin to fuse into helium. At this moment, when fusion begins, the protostar becomes a true star. But whether it becomes a small, long-lived dwarf or a vast, short-lived giant depends entirely on one thing: how much mass it starts with. If the collapsing cloud contains 10, 20, or even 100 times the mass of the Sun, the result will be a massive star, and its life will be intense, brief, and spectacular. Once a massive star ignites, it enters the main sequence, the long, relatively stable phase of its life, when hydrogen fusion powers the core. During this time, the energy produced by fusion pushes outward with just enough force to balance the inward pull of gravity. This equilibrium keeps the star from collapsing and also prevents it from expanding uncontrollably. But the balance is fragile. In a massive star, the fusion process occurs at incredibly high temperatures, and the core burns through its hydrogen supply at a furious pace. While a star like the Sun can remain on the main sequence for billions of years, a star with 10 times the Sun's mass may only last tens of millions. This speed of burning is a direct consequence of mass. Heavier stars are not just scaled-up versions of the Sun, they are fundamentally more extreme. Their cores are hotter, their luminosity far greater, and their fusion rates dramatically higher. In fact, a star that's only 10 times as massive as the Sun can be more than 10,000 times as bright. That energy must escape, and it does so by pushing on the star's outer layers, inflating them slowly over time. As the star ages, its core chemistry begins to change, and new processes begin, all driven by the same central balance between gravity and pressure. Massive stars are also shaped by their environment. They tend to form in clusters, surrounded by other young stars and active gas clouds. Their intense radiation and stellar winds can blow away nearby material, influencing the birth of other stars, and sometimes triggering new collapses in neighboring regions. But this brightness is a double-edged sword. The same energy that lets a massive star shine also begins to erode its structure. Over time, the radiation starts to drive stellar winds, streams of particles that carry mass away from the surface. These winds will eventually shape the next phase of the star's evolution. As the hydrogen in the core becomes depleted, the equilibrium starts to break down. The core contracts under gravity, growing hotter, while fusion begins in surrounding shells. The outer layers respond by expanding, and the star begins to shift in size, color, and internal structure. This is the end of the main sequence, and the beginning of something more unstable, a transition into the later stages of stellar life, when the balance becomes harder to maintain and collapse begins to loom. Massive stars live fast and die young. Their brilliance is not a sign of endurance, but of pressure, heat, and speed. The more mass a star has, the more rapidly it spends itself. And in the next stages of its life, that speed becomes a kind of unraveling, a race toward instability that no force can stop. Every star, no matter how vast it becomes, begins its life as a cloud. In the quiet arms of spiral galaxies or the dense knobs of stellar nurseries, there exist regions filled with cold molecular gas, mostly hydrogen, laced with traces of helium and heavier elements. These clouds can be immense, stretching across dozens or even hundreds of light years. But under the right conditions, gravity begins to pull the gas inward, causing it to clump, compress, and slowly collapse. Within these clouds, pockets form, denser regions called prestellar cores. And over time, if enough mass gathers, something remarkable begins to happen. The temperature rises. As the gas contracts, it heats. The atoms begin to collide more frequently, and the pressure at the center grows. Eventually, the core becomes hot and dense enough for hydrogen atoms to overcome their mutual repulsion and begin to fuse into helium. At this moment, when fusion begins, the protostar becomes a true star. But whether it becomes a small, long-lived dwarf or a vast, short-lived giant depends entirely on one thing: how much mass it starts with. If the collapsing cloud contains 10, 20, or even 100 times the mass of the Sun, the result will be a massive star, and its life will be intense, brief, and spectacular. Once a massive star ignites, it enters the main sequence, the long, relatively stable phase of its life, when hydrogen fusion powers the core. During this time, the energy produced by fusion pushes outward with just enough force to balance the inward pull of gravity. This equilibrium keeps the star from collapsing and also prevents it from expanding uncontrollably. But the balance is fragile. In a massive star, the fusion process occurs at incredibly high temperatures, and the core burns through its hydrogen supply at a furious pace. While a star like the Sun can remain on the main sequence for billions of years, a star with 10 times the Sun's mass may only last tens of millions. This speed of burning is a direct consequence of mass. Heavier stars are not just scaled-up versions of the Sun, they are fundamentally more extreme. Their cores are hotter, their luminosity far greater, and their fusion rates dramatically higher. In fact, a star that's only 10 times as massive as the Sun can be more than 10,000 times as bright. That energy must escape, and it does so by pushing on the star's outer layers, inflating them slowly over time. As the star ages, its core chemistry begins to change, and new processes begin, all driven by the same central balance between gravity and pressure. Massive stars are also shaped by their environment. They tend to form in clusters, surrounded by other young stars and active gas clouds. Their intense radiation and stellar winds can blow away nearby material, influencing the birth of other stars and sometimes triggering new collapses in neighboring regions. But this brightness is a double-edged sword. The same energy that lets a massive star shine also begins to erode its structure. Over time, the radiation starts to drive stellar winds, streams of particles that carry mass away from the surface. These winds will eventually shape the next phase of the star's evolution. As the hydrogen in the core becomes depleted, the equilibrium starts to break down. The core contracts under gravity, growing hotter, while fusion begins in surrounding shells. The outer layers respond by expanding, and the star begins to shift in size, color, and internal structure. This is the end of the main sequence, and the beginning of something more unstable, a transition into the later stages of stellar life, when the balance becomes harder to maintain and collapse begins to loom. Massive stars live fast and die young. Their brilliance is not a sign of endurance, but of pressure, heat, and speed. The more mass a star has, the more rapidly it spends itself. And in the next stages of its life, that speed becomes a kind of unraveling, a race toward instability that no force can stop. At the heart of every star is a crucible, a region where matter and energy are fused into something new. In the earliest and longest phase of stellar life, the dominant reaction is the fusion of hydrogen into helium. In smaller stars like our Sun, this occurs through a relatively gentle process called the proton-proton chain. But in more massive stars, the temperature and pressure are high enough to trigger a faster and more complex reaction known as the CNO cycle, named for the carbon, nitrogen, and oxygen nuclei that act as EBE catalysts. In this cycle, hydrogen nuclei collide and combine, forming helium and releasing vast quantities of energy in the process. As the star ages, the hydrogen in the core gradually runs out. When this happens, the balance between fusion pressure and gravity breaks. The core begins to collapse under its own weight, becoming hotter and denser. This triggers the next stage, helium fusion, where 3 helium nuclei combine to form carbon, a process known as the triple alpha reaction. From this point onward, the fusion process evolves into a layered sequence. Each new element created in the core becomes the fuel for the next round of reactions, and the core becomes surrounded by concentric shells of fusion, each burning different elements at different depths. In the most massive stars, this chain continues beyond carbon. As the core contracts and heats further, it begins to fuse carbon into oxygen, then oxygen into neon, neon into magnesium, and magnesium into silicon. Finally, the silicon fuses into iron, and that is where the sequence stops. Iron marks a hard limit. Unlike all the fusion reactions before it, turning iron into heavier elements does not release energy. Instead, it consumes energy. This means that once a massive star's core fills with iron, it can no longer sustain the pressure needed to resist gravity. Collapse becomes inevitable. This fusion process unfolds rapidly in a massive star's final stages. While hydrogen fusion may last for millions of years, each successive phase becomes shorter and shorter. Helium burning might last 1,000,000 years. Carbon fusion, only 1,000. Silicon fusion can happen in just a few days before the core collapses. It's as if the star burns faster the deeper it goes, racing through the periodic table with ever greater urgency. The layers become chaotic, turbulent, unstable, each shell of fusion pressing outward even as the iron core tightens. These fusion stages also determine the star's structure and appearance. Each reaction generates light and heat, contributing to the star's luminosity and internal convection. The result is a layered, glowing sphere with a seething, boiling atmosphere. But from the outside, these changes are not always visible. A hypergiant in its final days may look similar to how it did centuries earlier, though beneath the surface, nuclear chaos is reaching its peak. The energy produced by fusion doesn't just light up the star, it also defines its mass, brightness, and lifespan. This relationship is captured in a principle known as the mass-luminosity relation. It tells us that as a star's mass increases, its luminosity increases even more steeply, not in a straight line, but exponentially. For example, a star with 10 times the Sun's mass may shine with more than 10,000 times its brightness. This has profound consequences. The more luminous a star is, the more energy it radiates, and the faster it burns through its fuel. This relationship is part of why massive stars live such brief lives. Their internal engines are not just stronger, they are vastly more wasteful. While a small star can sip its hydrogen gently across billions of years, a massive star races through its reserves in just a few million. Its brilliance is a symptom of pressure and speed. It shines because it must, and it dies because it shines too much. If a star's life were measured in breaths, massive stars would inhale deeply, but only a few times. Their evolution unfolds across a timeline that feels strangely compressed, especially compared to the long, gentle arcs of smaller stars like our Sun. A star with one solar mass can remain on the main sequence for 10 billion years. But increase that mass to 10 solar masses, and the timeline shortens drastically down to 20 or 30 million years. Raise it again to 30 or 40 solar masses, and the star's life may last only a few million years in total. The most massive stars we've discovered may burn out entirely in less than 1 million years. To human eyes, these are still vast lengths of time, but in cosmic terms, they are fleeting. These stars form quickly, shine intensely, and die young. A red supergiant like Betelgeuse has likely existed for only a fraction of the Sun's age. A hypergiant like Stephenson 2 may have lived for mere millions of years and may already be approaching its end. From birth to collapse, these stars are in constant motion, fusing and radiating at a furious pace. Their brightness is not a sign of longevity, but of pressure, an internal urgency to keep gravity at bay. The reason these lifespans shrink so dramatically is rooted in how energy is produced and used. Fusion in the core must supply enough outward force to counteract the star's enormous gravity. But the more massive the star, the stronger that gravity becomes, and the more energy must be generated to keep the star stable. As a result, the fusion rate accelerates. Hydrogen is converted to helium, not slowly and gently, but in great waves of heat and pressure, producing intense luminosity and tremendous stellar winds. The star shines brilliantly, but burns through its fuel in the process. This process is not linear. It's exponential. A star that is twice as massive as another does not merely burn twice as fast, it can burn 10 or even 100 times as fast. That's because fusion output depends not only on mass, but on temperature and pressure at the core, which increase steeply with mass. These core conditions trigger more energetic reactions, which in turn produce more radiation. That radiation pushes on the star's outer layers, causing it to expand and shed mass, but it also pushes outward at the atomic level, driving the fusion that powers the star. As the star grows larger and more luminous, it also becomes more fragile. Its own energy output begins to destabilize the envelope. Radiation pressure overcomes gravity in the outer layers, and material begins to drift away. What began as a powerful engine of creation starts to unravel. Even as the core continues to burn, the star's mass begins to decline, carried off by stellar winds and outbursts. Over time, the star loses a significant portion of its original mass, yet still burns hotter, fuses faster, and marches steadily toward collapse. This is the paradox of massive stars. The very mass that gives them their brilliance also ensures their early death. They burn with extraordinary power, shaping galaxies, seeding the cosmos with light, but they cannot sustain themselves. The more fuel they contain, the more quickly it is consumed. And when the fuel is gone, gravity takes over, and the final transformation begins. For now, though, these stars are still shining, still burning through their lives in a cascade of fusion reactions, throwing light and heat into the void. But deep inside, the timer is already running down, and the layers of the star are shifting into the next phase. As a massive star ages, the balance it once held so tightly begins to fray. Its core is burning faster than ever, its mass shifting inward, and its atmosphere, once stable, starts to drift away. This process begins quietly, almost invisibly, as stellar winds rise from its surface. These winds are not like the breezes we feel on Earth. They are streams of particles, atoms and ions, pushed outward by the sheer intensity of radiation. Driven by light itself, they move through space at speeds of hundreds or even thousands of kilometers per second. Over time, they carry away staggering amounts of material. This steady loss of mass can alter the course of the star's evolution. For red supergiants and hypergiants, the rate of mass loss increases dramatically in the final stages of life. A star like VY Canis Majoris may shed as much as 1 Earth mass every year. Over the course of its dying phase, it can lose more than half of its total mass, gas and plasma that once helped it resist collapse, now floating outward into the interstellar medium. These stellar winds don't just thin the atmosphere, they reshape it, creating vast halos and arcs of drifting material that glow in infrared and radio light. But mass loss isn't always smooth. The outer layers of a dying giant can become unstable, moving in waves and pulses that ripple across the star's enormous surface. These pulsations are caused by internal changes, sudden shifts in energy flow, convection currents, or partial collapses within outer fusion shells. When the pressure builds, the star expands slightly and then contracts again, like a slow heartbeat. These pulses can take months, even years, to complete. But with each one, the outer atmosphere is pushed outward, sometimes far enough that gravity can no longer pull it back. The result is episodic mass loss, sudden shedding of gas into the surrounding space. Convection also plays a critical role in this stage. Inside the outer layers, enormous bubbles of hot gas rise from deeper within the star, carrying energy toward the surface. These convection currents can be massive, spanning entire percentages of the star's diameter. As the hot gas reaches the top, it cools and sinks again, setting up churning, rolling motion throughout the envelope. In a red hypergiant, this convection can become turbulent, breaking the surface in the form of bright spots or cold patches. The surface is no longer smooth or static. It boils. This boiling can drive further instability. A convection plume might briefly increase local brightness, changing the pressure in that region and triggering the ejection of material. In some cases, these outbursts can be strong enough to form visible structures, arcs, loops, or faint nebulous shells that move away from the star over time. These structures are sometimes captured by infrared telescopes as infrared arcs or bow shocks, created as the star's expelled material collides with the surrounding interstellar gas. With each loss of mass, the star becomes lighter, but not necessarily more stable. The loss is uneven, and the internal layers remain under extraordinary pressure. The surface is stretched thin, tugged outward by radiation and inward by gravity, but never quite able to hold its shape. The star enters a period of slow unraveling. Its size may continue to increase, even as its outer envelope begins to evaporate into space. And yet, this loss of mass is not an ending. It's a transformation. The material being shed will not disappear. It will become part of the galaxy once again, feeding new stars, forming clouds, shaping dust and future systems. Even as the hypergiant loses its grip, it is still giving something back to the cosmos. As mass continues to leave the star, its outer layers grow thinner, more fragile, and vastly more extended. What we might once have called the star's surface no longer exists in any simple way. Instead, the outer atmosphere becomes a vast, diffuse envelope of gas and plasma, spreading outward into space. In a star like Stephenson 218, this envelope may stretch across hundreds of millions of kilometers, with no clear edge, just a slow fading from dense inner layers to nearly invisible wisps at the boundaries. The atmosphere is not a shell, but a gradient, and it is constantly in motion. These extended atmospheres are incredibly unstable. They are shaped by convection, radiation, and turbulence, and they fluctuate over time. Regions of the atmosphere may brighten or dim, expand or contract, or peel away entirely. Internal pressure waves, driven by changes in the core's fusion rate, can ripple outward, disturbing the delicate balance between gravity and outward force. And because the material is so loosely bound, even small disturbances can lead to large-scale ejections. The result is an atmosphere that flickers and flows, like a slow-motion storm system stretched across the scale of a solar system. In these conditions, new structures begin to form around the star. As gas is expelled and drifts outward, it begins to cool and condense into circumstellar envelopes, loosely bound regions of gas and dust that surround the star like a shroud. These envelopes can extend far beyond the visible glow of the star itself, sometimes reaching many thousands of times the star's own radius. They are not part of the star in the traditional sense, but neither are they separate. They represent a kind of middle ground, material that once belonged to the star, now suspended in orbit around it, glowing softly in the infrared. The composition of these envelopes tells a story. Some are rich in oxygen, others in carbon. Some contain tiny crystals of silicate or graphite, formed from the cooling gases ejected from the star. Still others include complex molecules, including water, carbon monoxide, and even simple organic compounds, all drifting in the outer reaches of a dying star's influence. These materials, shaped by fusion and heat, are now drifting back into space, where they may one day become part of planets, moons, or other stars. When we observe these envelopes through infrared or radio telescopes, we often see them as clouds, arcs, or shells, faint structures that surround the central star like ripples in a pond. In some cases, these arcs are uneven, shaped by previous eruptions or by interactions with other nearby stars. In binary systems, the winds from one star may push against the other, sculpting the envelope into spirals or sweeping it into long tails. These structures are often invisible in ordinary light, but with the right instruments, they reveal a record of the star's final centuries. Over time, these circumstellar structures can evolve into full-fledged nebulae. If the star's core eventually collapses and sends out a powerful shockwave, the expelled material can be pushed even farther, glowing in response to the heat and radiation from the explosion. This is how many of the most beautiful nebulae we see today were formed, from the extended envelopes of dying stars, lit from within by the aftermath of collapse. But even before that final moment, the formation of these structures is already underway. The process is both chaotic and elegant. A star nearing death sheds itself layer by layer, not all at once. The material that leaves is not waste. It is the star's legacy. It carries with it the fingerprints of fusion, the temperature of ancient cores, the elements forged in fire. And out in the darkness, these drifting clouds mark the slow departure of a giant. Even though the outer layers of a dying giant become too faint and diffuse to see directly, astronomers have developed powerful tools to study them. They read the light. As the star shines, its light passes through its own atmosphere, and in doing so, it leaves behind a signature, a complex fingerprint of elements, motion, and structure. This is the science of stellar spectroscopy. By splitting the star's light into its component wavelengths, scientists can detect the presence of specific atoms and molecules, the velocities of moving gas, and even the density and temperature of distant layers that no eye can see. Each element absorbs light at specific wavelengths. When that element exists in the star's atmosphere, it leaves behind absorption lines, narrow gaps in the spectrum where light has been absorbed. The strength, shape, and position of these lines tell us a great deal. A broadened line might indicate fast movement or turbulence. A red-shifted line reveals gas flowing outward, away from the star. A blue-shifted one suggests material falling inward or cycling through convective layers. By analyzing these features, astronomers can map the dynamics of a hypergiant's outer envelope in surprising detail, even from across thousands of light-years. In the case of stars like VY Canis Majoris, Betelgeuse, or UY Scuti, spectral observations have revealed pulsation cycles, zones of mass ejection, and complex molecular chemistry. Molecules like water vapor, silicon monoxide, and carbon monoxide have all been detected in their outer atmospheres, despite the high temperatures and low pressures. In cooler regions, these molecules survive long enough to emit light of their own in infrared and radio wavelengths. Observing that light gives scientists a window into the slow unraveling of the star and into the fate of the material it releases. These studies don't just tell us about the star itself. They also reveal how the fading giant interacts with the space around it. As mass drifts outward, it doesn't simply vanish. It collides with the interstellar medium, the diffuse gas and dust that fills the galaxy, and leaves a mark. In some cases, this creates shock fronts, boundaries where the star's winds pile up against the surrounding gas, heating it and compressing it into arcs or filaments. These structures are often invisible in visible light, but glow brightly in the infrared or ultraviolet, allowing astronomers to trace the star's long-term influence. The star's radiation also affects nearby space. Intense ultraviolet light can ionize surrounding hydrogen, creating faint bubbles of ionized gas. These the second regions, named for ionized hydrogen, are commonly seen around young, massive stars, but older giants can produce similar effects as they die. Even low-density envelopes can reflect, scatter, or reshape light from the star, creating a glowing halo that extends far beyond the core. These effects may seem subtle, but they represent a powerful force. A single hypergiant can reshape its surroundings across light-years of space. In regions where other stars are forming, the influence can be even more profound. The shock waves and winds from a dying giant can compress nearby clouds, triggering the collapse of gas into new stars. In this way, the death of one star becomes the catalyst for many others. This process of triggered star formation is believed to play a major role in the structure of stellar nurseries and the evolution of galaxies. It is part of the cosmic cycle, the constant exchange of matter and energy from one generation of stars to the next. So even as the star's atmosphere becomes thin and unstable, its reach grows wider. The gravity that once held its mass in place has loosened. The energy that once pushed outward now drives material far beyond its former edges. In this quiet unraveling, the star becomes not just a dying object, but a shaper of space, a sculptor of the interstellar medium, and a bridge between past and future. At the end of its long and burning life, a massive star becomes layered like an onion. Hydrogen fusion has long since moved outward, replaced by concentric shells of helium, carbon, oxygen, and heavier elements, each burning briefly before giving way to the next. At the very center, the star's core contracts under its own weight, becoming hotter and denser with each passing moment. Eventually, the core begins to fuse silicon into iron, the last act in the long chain of nuclear reactions. And here, the process stops. Not just slows, but stops entirely. Because unlike the fusion of lighter elements, fusing iron absorbs energy. It takes more energy to force iron nuclei together than the reaction releases. For a star, this is a catastrophic change. The iron core grows rapidly, fed by layers above, and supported only by the intense pressure of degenerate electrons, the same quantum pressure that holds up white dwarfs. But there's a limit to how much mass even that pressure can withstand. As the core approaches around 1.4 times the mass of the Sun, a boundary known as the Chandrasekhar limit, the balance breaks. There is no new fuel to ignite, no outward force to resist collapse. The star has built its own undoing. It has created a core it can no longer support. In that moment, gravity, always patient, always waiting, takes over. With no more fusion pressure to oppose it, the iron core begins to collapse inward at merely a quarter the speed of light. In less than a second, it shrinks from the size of a planet to the size of a small city. The electrons that once provided pressure are forced into atomic nuclei, combining with protons to form neutrons. This process, called electron capture, releases a sudden burst of neutrinos, tiny, ghost-like particles that escape the core in vast numbers, carrying away energy. The collapse is not gentle. It is a gravitational catastrophe. Infalling material crashes inward, piling into a dense neutron core that rapidly stiffens. This abrupt deceleration sends a shockwave outward, the first tremor of what will become a supernova. But for now, deep inside the star, the collapse is still ongoing. The outer layers are unaware. Light from the core's final moments hasn't even begun to escape. The star still appears intact from afar. But inside, the transformation has already begun. The pressures and densities inside the collapsing core are unimaginable. In less than a second, the core reaches a density greater than that of an atomic nucleus, more than 10 trillion kilograms in every cubic centimeter. At this scale, atoms no longer exist. Matter becomes a sea of neutrons, compressed to the brink of physics itself. If the collapsing core contains enough mass, even this neutron pressure will fail, and the core will continue falling, forming a black hole. But if the mass remains just under that limit, a new object is born, a neutron star, so dense that a single teaspoon would weigh more than Mount Everest. While the core collapses, the outer layers begin to respond. They too are pulled inward, rushing toward the center. But the core's sudden rebound, the formation of the neutron core and the emission of neutrinos, begins to push back. A shockwave builds and starts to move outward. Still, for a brief time, the interior is in chaos. The collapse phase is short, but what happens in those milliseconds will determine the star's fate, whether it will explode, implode, or disappear entirely. This is the moment where time and pressure fold in on themselves. The star, which has burned for millions of years, now races through its final breath. Its center has become a furnace of exotic physics. And yet, from the outside, nothing has changed. The light from the surface still shines with the same red glow. The winds still drift gently outward, but deep within, the collapse is already in motion, and there is no force in the universe that can stop it. As the iron core collapses inward, it accelerates under the immense pull of gravity. There is no resistance left, no fusion pressure, no internal energy to push back. In the final fraction of a second, the core implodes catastrophically. The matter inside falls freely, gaining velocity, shrinking in scale. From thousands of kilometers across, the core contracts down to just tens. Electrons are forced into protons, and protons are crushed into neutrons. At this point, the laws of quantum physics take over. The neutrons resist further compression with a force called neutron degeneracy pressure, the last line of defense before a black hole. When the imploding matter reaches nuclear density, the collapse slams to a halt. The infailing material strikes the solid core, a mass of neutrons packed tighter than anything in the known universe, and the result is an extraordinary rebound. This sudden stop produces a violent wave of pressure that races outward through the collapsing layers of the star. It is known as the core bounce, the moment the star's interior punches back against its own fall. But this bounce alone isn't enough to cause the supernova. Most of its energy is lost, absorbed by the surrounding material. The shock wave stalls. The missing ingredient is already on its way, a flood of neutrinos. During the collapse, trillions upon trillions of these nearly massless particles are produced, each carrying away a tiny fraction of energy. Though they rarely interact with matter, the density in the star's core is so high that a small portion of these neutrinos do collide with atomic nuclei in the outer layers. This transfer of energy reinvigorates the stalled shockwave, pushing it outward with new force. In a fraction of a second, the inner star is transformed, from quiet collapse to outward explosion. This neutrino-driven mechanism is one of the most important and least visible steps in the life of a dying star. The sheer number of neutrinos involved is staggering. In a typical core collapse event, more than 10 to the power of 58 neutrinos are released. That's a 1 followed by 58 zeros. Almost none of them reach Earth. But a few do, and in rare moments, detectors here on our planet catch them. This is how we first knew about the collapse of supernova 1987A, not from light, but from a handful of ghost-like particles that arrived hours before the explosion became visible. The bounce and the neutrinos together generate the shock wave that begins to tear the star apart. As the wave moves outward, it heats the overlying layers, vaporizing elements, disintegrating atoms, and blasting the material into space. The shock wave travels at extraordinary speed, ripping through each shell of the star's structure. What took millions of years to build is now being unmade in seconds. The star is entering its most dramatic moment, a brilliant final flash that will echo across space for centuries. And yet, most of this story remains invisible. The neutrinos do not glow. The bounce makes no sound. Even the first stages of the shock wave are hidden deep inside the star's atmosphere. From the outside, the red glow continues for just a little while longer. But inside, the explosion has begun. The structure is coming apart. The collapse is becoming an event that will reshape the surrounding space and leave behind a remnant unlike anything else in the galaxy. This process, from core implosion to bounce to shockwave, happens in less than a second. It is one of the most violent and consequential transformations in the universe, and yet it occurs in perfect silence. Light has not yet reached the surface. The star has not yet vanished. But deep within, its final act is underway. In the milliseconds before a supernova becomes visible, the internal structure of the star reaches its most critical state. The shock wave, newly revived by the rush of neutrinos, is tearing outward from the core. Behind it is a freshly formed neutron star, just moments old, spinning rapidly and radiating with raw gravitational energy. Ahead of it are layers upon layers of still collapsing material, each with its own density, velocity, and inertia. The wave slices through these regions, heating them to extreme temperatures, igniting brief moments of fusion and unraveling every last boundary the star once held in place. At this scale, the movement of energy becomes chaotic. Gamma rays burst forth, nuclei are shattered and reassembled, and new elements are forged in an instant. Iron breaks apart. Lighter nuclei collide in the heat and reform into nickel, cobalt, and other heavy metals, a process called explosive nucleosynthesis. These elements, destined to scatter into the galaxy, are born in less time than a human heartbeat. The physics here is beyond intuition. Forces stronger than any machine we've ever built are operating across distances measured in kilometers and across timescales measured in fractions of a millisecond. And then, the shockwave reaches the star's outer edge. In that moment, the star's light changes. After millions of years of steady fusion and months of quiet unraveling, the star begins to brighten. The visible supernova has arrived. A flash of radiation bursts outward, followed by a sustained increase in brightness that may last for days or weeks. But for all its brilliance, what we're seeing is already the aftermath of the core's collapse. The true moment, the one when the star transformed itself, is already in the past. At the center of this collapse, time itself behaves differently. As the core contracts and its gravity intensifies, it begins to warp space-time around it. This effect, predicted by general relativity, means that time slows down near objects with extreme gravity. For an outside observer, the collapse appears to proceed normally. But for a particle or a photon, deep inside the gravitational well, time ticks more slowly. If the core becomes a black hole, this time dilation becomes even more dramatic. In theory, the final moments of collapse could stretch toward infinity, frozen at the edge of the event horizon. Even before that threshold is reached, time dilation plays a measurable role. Neutrinos that escape from the collapsing core arrive at Earth before the light does, not just because they move ahead of the shockwave, but because the light itself is delayed by layers of plasma and by the effects of extreme gravity. The deeper into the star you go, the more slowly time passes, compared to the outer regions or to a distant observer in space. This means that the collapse happens in different rhythms depending on your vantage point. A star's death is not one moment, but many, stacked and curved by the warping of space and time. This slowing of time doesn't stop the collapse, but it adds another layer of mystery to what is already one of the most complex events in nature. When we observe a supernova from afar, we are seeing only the bright outer echo of an event that took place deep within a distorted space-time. We can model the physics, measure the light, and capture the neutrinos. But the collapse itself, the pure interior moment when a star becomes something else, is forever hidden behind distance, gravity, and time. And so, just before the explosion appears, the core is already gone. The collapse has happened. The rebound has passed. The wave is on its way out. And time, for a moment, has bent in quiet reverence around the dying star. When the shockwave breaks through the star's surface, the transformation is complete. What began as a quiet gravitational collapse now becomes a supernova, a cosmic explosion so powerful that, for a brief time, a single star can outshine an entire galaxy. The light reaches across millions of light years. To distant observers, it appears suddenly a new point of brilliance in the sky, where once there was only darkness. But the brightness is not from the core. It comes from the outer layers, now ripped apart and hurled into space at speeds of tens of thousands of kilometers per second. This is a core-collapse supernova, the explosive end of a massive star. It marks the release of energy that was once bound in fusion, now liberated in a fraction of a second. The explosion itself is not a single flash, but a complex unfolding. There is an initial burst of light, the shock breakout, followed by a longer glow, powered first by the kinetic energy of the blast and later by radioactive decay. Elements created in the final milliseconds, like nickel-56, decay into cobalt and iron, releasing gamma rays that heat the expanding gas and prolong the star's final illumination. The shockwave carries with it matter and momentum, crashing through each shell of the star and vaporizing what remains. The once stable layers of hydrogen, helium, carbon, and oxygen are torn apart, reshaped, and flung outward into the vacuum of space. This expanding cloud of debris is hot, dense, and glowing. And as it cools, it will begin to reveal the chemical legacy of the star, the ashes of fusion, now drifting freely. Every atom of calcium in your bones, every bit of iron in your blood, was once formed in such a moment, in the death of a giant. Alongside the explosion comes an invisible storm. In the seconds after the collapse, the star emits a flood of neutrinos, more than 100 times the number of atoms in the observable universe. These neutrinos, though almost massless, carry away most of the energy released by the event. Only a small fraction escape detection, but those few give scientists the earliest signs that a supernova has occurred. Long before the light arrives, before the gas begins to glow, a tiny signature appears in underground detectors on Earth, a flicker from the ghosts of a dying star. The expanding shockwave also leaves behind a signature in the surrounding space. As it moves outward, it sweeps up interstellar dust and gas, compressing it into shells or rings, heating it into filaments that glow in ultraviolet and X-rays. These shock fronts, sometimes hundreds of light years across, can last for tens of thousands of years. In some cases, they become visible as supernova remnants, complex webs of gas and dust that continue to radiate long after the star has disappeared from view. As the debris expands, it begins to cool. The visible light fades, and the star's final glow gives way to infrared and radio emissions. But within this fading light are clues to the explosion itself, clues that astronomers use to reconstruct what happened. The velocity of the ejected material, its composition, its temperature, all tell part of the story. No two supernovae are alike. Some leave behind neutron stars, others collapse further into black holes. Some explode symmetrically, while others erupt with lopsided force, launching material in arcs or jets. What remains is not a grave, but a transformation. The star is gone, but its materials are scattered, its energy redistributed, its light traveling outward, still crossing the galaxy. The shockwave may trigger new stars to form. The heavy elements may seed future worlds. The neutrinos may pass silently through planets, bodies, and dust, never stopping, never aging. The explosion is final, but its consequences are just beginning. At the center of the explosion, hidden behind the expanding cloud of debris, something extraordinary has formed. After the collapse and bounce, after the outer layers have been blasted away, what remains is the stellar core. Once the engine of fusion, now compressed into a new and alien object. If the mass is modest, less than about twice that of the Sun, the core becomes a neutron star, an object so dense that a single teaspoon would weigh more than 1 billion tons. It is made almost entirely of neutrons, bound together by gravity and quantum pressure, spinning rapidly and radiating with invisible light. Neutron stars are among the strangest known objects in the universe. Some rotate many times per second, sending beams of radio waves through space like cosmic lighthouses. These are called pulsars. Others have intense magnetic fields, thousands of times stronger than anything Earth has ever experienced. These are magnetars, capable of emitting powerful bursts of gamma rays in sudden, unpredictable flares. The surface of a neutron star is solid, but only a few centimeters thick. Beneath it lies a core so dense that atoms no longer exist, only particles in quantum states beyond our full understanding. But if the original star was even more massive, if the collapsing core exceeds the limit that neutron pressure can resist, the result is not a neutron star. It is a black hole. In this case, the core continues to collapse past every known physical boundary, compressing into a point of infinite density surrounded by an event horizon, the region beyond which nothing, not even light, can escape. Black holes are silent. They leave no surface behind, no echo of structure. Only their gravitational influence and the absence of light reveals their presence. In the heart of some supernova, this is the final destination, a star that ends not in light, but in darkness. Even as the central object forms, astronomers around the world begin to study the explosion itself through its light curve, a graph of brightness over time. Each type of supernova produces a different light curve, shaped by the explosion's energy, the elements involved, and the mass of the ejected material. In the case of a core-collapse supernova, the light usually peaks quickly, then fades slowly over weeks or months. The early brightness comes from the shock breakout and the heating of the outer layers. Later light comes from the radioactive decay of elements like nickel and cobalt. These decays release gamma rays, which are absorbed by the expanding gas and re-emitted as visible light. As the gas thins and cools, the light fades. But even in this fading, scientists can measure the amount of material ejected, estimate the star's original mass, and even infer what type of remnant was left behind. Some supernova, like type 2P, show a characteristic plateau in brightness, a sustained period where the light remains nearly constant before dropping off. Others, like type IB and IK, show sharp rises and faster declines, often indicating the absence of hydrogen or helium in the outer layers. These light curves are more than just pretty graphs. They are windows into the physics of a dying star. Combined with spectral analysis, they tell a story. Which elements were present, how fast the debris is moving, and how much energy was released. In some cases, a secondary peak in the light curve may reveal interactions between the ejected material and surrounding gas, a sign that the star had been shedding mass before the explosion, building up a dense envelope of material now being shocked and lit from within. Observing these events requires precise timing and patience. Many supernova are found days after they begin, their early light already faded. Others are caught early, revealing details about the shock breakout or the rise in brightness. Telescopes around the world and in orbit now monitor galaxies constantly, watching for these sudden bursts of light. When one appears, a global network of observers turns their instrument toward it, capturing every possible signal, light, neutrinos, gravitational waves, in an effort to understand what happened inside. And so, long after the star has collapsed, its light continues to teach us. In the patterns of fading brightness, in the rhythms of radiation, we find traces of what occurred deep inside, of what was created, what was lost, and what remains. When the explosion is over and the light begins to fade, the story is not yet complete. What remains behind The fragments, the glowing gases, the collapsed core, becomes a new kind of structure, a supernova remnant. These remnants are some of the most beautiful and haunting objects in the sky. They are the final shape of a star's death, sculpted by shockwaves, illuminated by radiation, and traced by the paths of high-energy particles. Over time, they expand into delicate webs of gas and dust, glowing in X-rays, visible light and radio waves. Each is unique, shaped by the mass of the star, the force of the explosion, and the medium it expands into. Some remnants take the form of glowing nebulae, shells or filaments of gas spreading outward in loops and spirals. The Crab Nebula, for instance, is the remnant of the supernova observed on Earth in the year 1054. It still expands today, nearly 1,000 years later, and at its center lies a spinning neutron star, a pulsar, emitting regular bursts of energy as it rotates. These pulses, arriving every 33 milliseconds, are the heartbeat of the dead star. Though the surface is gone, the rhythm remains. Other neutron stars are even more extreme. Magnetars, a rare subclass of neutron stars, possess magnetic fields trillions of times stronger than Earth's. These fields can twist and rupture, releasing enormous flares of X-rays or gamma rays in events that may last only seconds, but carry more energy than our sun emits in a century. Magnetars are unstable, unpredictable, and difficult to detect, but they are among the most powerful remnants left behind by stellar collapse. They do not shine like normal stars. They reveal themselves in flashes, in silence, and in radiation that passes invisibly through the galaxy. Each remnant carries the signature of its origin. The composition of the gas, the pattern of expansion, and the structure of the shock front all preserve details about the explosion. In some cases, the remnants are nearly spherical, as if the star had died in perfect symmetry. In others, they are lopsided or elongated, suggesting rotation, magnetic influence, or asymmetries in the collapsing core. Over time, these shapes evolve. The gas spreads out, cools, and mingles with the interstellar medium, but the remnant remains detectable for tens of thousands of years. These remnants are more than ruins. They are active agents in the life of a galaxy. The material they carry, rich in heavy elements like iron, nickel, calcium, and silicon, becomes the raw material for future generations of stars and planets. The energy they release stirs the interstellar gas, triggers waves of compression, and helps define the shape and motion of spiral arms. A single supernova can reshape entire regions of space, disrupting or enriching clouds across dozens of light years. In the long view, the legacy of a supernova is not destruction, it is creation. Without these explosions, the universe would lack the elements necessary for life. The carbon in your cells, the oxygen in your lungs, the iron in your blood, all were forged in ancient stars and released by explosions like these. The death of a massive star is not the end of the story. It is a turning point, the beginning of something new. And even after the remnant fades, the effects remain. Shock waves echo through the galaxy. Magnetic fields ripple outward. New stars begin to form in clouds touched by the blast. In this way, the memory of the supernova is written not just in the dust it leaves behind, but in the stars that come after. Stars that shine with borrowed atoms and inherited light. The death of a massive star is not just a dramatic ending, it is a kind of alchemy. Inside the core, and especially in the moment of its collapse and explosion, the star becomes a forge. It transforms the simplest element, hydrogen, into a rich spectrum of heavier elements, from helium and carbon to iron, nickel, and beyond. This process is known as nuclear synthesis, and it is one of the primary ways the universe builds its complexity. Without it, the cosmos would be a cold and empty sea of hydrogen and helium, with no planets, no rocks, no water, and no life. Most of the fusion that occurs during a star's life creates elements up to iron. But in the final moments, when the core collapses and temperatures spike to billions of degrees, a new type of nucleosynthesis begins. This is explosive nuclear synthesis, triggered by the supernova shockwave. In these extreme conditions, atoms are shattered and recombined, and neutron capture reactions begin. Free neutrons, released in the chaos, are absorbed by atomic nuclei, which then decay into new elements. This is how many of the universe's heaviest elements, such as gold, platinum, uranium, and rare earth metals, are formed. This particular process, called the rapid neutron capture process, or R process, requires enormous densities and a flood of neutrons, conditions that only supernova or neutron star collisions can provide. When we hold a gold ring or a trace of iodine in our bodies, we are touching the remnants of a long-dead star. The carbon that forms the backbone of life, the calcium in bones, the oxygen in every breath, all were born in stellar cores and scattered by explosive death. Every supernova adds to this richness, spreading heavy elements across the cosmos. Once expelled, these elements begin a new journey. The gas and dust from a supernova do not remain isolated. Over time, they are swept up into interstellar clouds, the vast cold nurseries where new stars are born. The presence of these heavy elements, called metals by astronomers, changes the chemistry of the galaxy. A cloud enriched by the death of previous stars can cool more efficiently, collapse more quickly, and form more complex structures than a cloud of pure hydrogen and helium. This seeding process turns a simple universe into a layered one. In the earliest galaxies, stars were composed almost entirely of hydrogen and helium. But as more stars died, the metal content of the galaxy increased. Today, nearly every star we see, including our Sun, contains a measurable amount of heavier elements. These trace components affect how stars shine, how planets form around them, and how atmospheres evolve. Metal-rich stars tend to form rocky planets, while metal-poor stars may lack the materials needed for terrestrial worlds. The material released by supernova also influences the structure of star-forming regions. Shockwaves from the explosion can compress nearby gas clouds, triggering the formation of new stars. At the same time, the heavy elements within the debris enrich the surrounding medium, ensuring that the next generation of stars and their planets will be chemically different from the last. This cycle continues over billions of years, gradually increasing the complexity and variety of objects in the galaxy. We can even trace this enrichment through stellar archaeology. By analyzing the composition of old stars, scientists can infer the types of supernova that came before them, their energies, their masses, and the elements they contributed. These chemical fingerprints are like time capsules, revealing the invisible histories of regions we can never visit. So while the explosion of a giant star may seem like an ending, it is better understood as a kind of distribution system, scattering the building blocks of future worlds across vast stretches of space. It is how the universe takes what it has made, breaks it apart, and reshapes it into something new. Massive stars do more than illuminate the night sky. They shape the very structure of the galaxies they inhabit. Through their lives, and especially through their deaths, they inject energy, matter, and momentum into their surroundings. This process, often referred to as stellar feedback, plays a critical role in galaxy evolution. It determines where stars form, how gas flows, and even how spiral arms are maintained over billions of years. Without the presence of massive stars, galaxies would look very different, more uniform, more stagnant, and far less structured. When a massive star explodes, it sends shock waves through the interstellar medium. These waves compress gas clouds, triggering star formation in some places, while dispersing clouds in others. Over time, this feedback balances the rate at which stars form, preventing galaxies from collapsing too quickly or burning through all their gas at once. In this way, supernovae help regulate the life cycles of galaxies. They are both creators and disruptors, stirring the cosmic soup with each brilliant detonation. In starburst galaxies, where stars form rapidly, the combined influence of many supernovae can create galactic winds, powerful outflows of hot gas that stream away from the central regions into intergalactic space. These winds carry metals and energy into the vast emptiness between galaxies, helping to enrich the cosmic web itself. In this sense, the death of a star is not confined to its local environment. It can have intergalactic consequences, shaping structures on scales far beyond its original system. But not every stellar death is the same. Some are far more violent, far more extreme. In rare cases, a massive star may collapse with such intensity that it produces a hypernova, an explosion 10 or more times more energetic than a typical supernova. These events are thought to occur in very massive, rapidly spinning stars, possibly stripped of their outer hydrogen layers. The core collapses into a black hole, and in the process releases not just a massive explosion, but something even more exotic, a gamma-ray burst. Gamma-ray bursts, or GRB, are the most energetic events known to occur in the universe. They appear as sudden flashes of high-energy gamma rays, lasting anywhere from milliseconds to several minutes. In those brief moments, a single burst can outshine every other source of gamma rays in the sky combined. These bursts are often accompanied by a visible afterglow, a fading signature across X-ray, optical, and radio wavelengths. But the gamma rays themselves come from relativistic jets, narrow beams of energy launched from the poles of the collapsing star at nearly the speed of light. Not every supernova produces a gamma-ray burst. The conditions must be just right: rapid rotation, extreme mass, a collapsing core forming a black hole, and the right angle of observation. But when they do occur, the result is astonishing. The energy released in just a few seconds can rival the total output of the Sun over its entire lifetime. And although most GRBs happen far away, in distant galaxies billions of light-years from Earth, their power is unmistakable. They are brief, but their effects can last for millennia. Scientists continue to study GRBs in hopes of understanding the environments that produce them. Some appear to result from massive stars collapsing in isolation. Others may come from mergers of neutron stars, another path to cosmic violence. In either case, they represent the outer edge of what a star can become, the most extreme form of stellar death. And while rare, they may have played key roles in shaping early galaxies, influencing the chemistry of the universe, and even, in theory, affecting biological evolution on Earth through bursts of radiation from deep space. So, in the grand scale of things, giant stars do not merely live and die. They sculpt galaxies, launch winds, trigger storms, and ignite the brightest lights in the cosmos. Their influence extends from the heart of their own systems to the structure of the universe itself. Among the rarest and most extraordinary stellar deaths are those known as parent stability supernovae. These events occur only in the most massive stars, typically those with initial masses between 100 and 150 times that of the Sun. In such stars, the core becomes hot enough that the energy of light itself begins to transform. Photons in the high-energy core can spontaneously convert into electron-positron pairs, reducing the radiation pressure that had once supported the star from within. In a sudden and dramatic shift, the balance breaks and the core partially collapses. This collapse causes a burst of new fusion, igniting the fusion of oxygen or silicon explosively. But instead of stopping with a rebound, as in a typical core collapse supernova, the energy released is so intense that it completely unbinds the star. No neutron star or black hole remains. The star is blown apart in a single massive detonation, leaving only a vast expanding shell of enriched gas. This is the signature of a true parent stability supernova. Total annihilation, with nothing left behind but light and dust. Such explosions are thought to have been more common in the early universe, when metal-poor, first-generation stars known as population the third stars may have reached the enormous masses needed for this process. In today's universe, they are vanishingly rare. But astronomers continue to search for their signs. Unusually bright supernova with distinctive light curves, indicating extreme energy and an absence of any remnant. If confirmed, these events would offer a glimpse into the lives of the first stars and into a form of stellar death almost lost to time. Even when stars die less dramatically, they contribute to something profound: the cosmic recycling of matter and energy. Every element a star produces, every atom it sheds, becomes available to the universe once again. The hydrogen that fused into helium, the carbon and oxygen cast off into space, the iron and nickel formed in the final explosion. All of it becomes part of the interstellar medium, drifting through gas clouds, caught in gravitational eddies, folded into new solar systems. This recycling is not a side effect of stellar life. It is the engine of cosmic evolution. The matter that once burned in a hypergiant's core might eventually find itself locked in the crust of a rocky planet, or suspended in a comet, or folded into the atmosphere of a young exoplanet. Over and over again, the materials of stars are remade. What explodes in one moment becomes the seed of something new in another. Energy, too, is passed along. The light of a dying star travels across galaxies. The heat of an expanding remnant stirs nearby clouds. Neutrinos and cosmic rays scatter in all directions, whispering messages from distant deaths. Even gravity plays a role, the ripples of collapse spreading outward, shaping orbits, stretching space-time, marking the transformation of mass into motion. In this way, the universe never truly loses anything. It rearranges. It recycles. It keeps the elements in motion, the light in transit, the stories unfolding. A single massive star may shine for a few million years, but its influence endures far beyond that. It lingers in light and dust, in memory and matter, in the quiet curves of galaxies and the iron in a sleeping planet's core. And perhaps, in the distant future, the atoms released by today's stars will find themselves in new forms, not just in stars and planets, but in life. In eyes that watch the stars, in hands that build telescopes, in minds that wonder where it all began. The light of a star is not just a glow in the darkness, it is a slow, patient offering. A quiet transformation of matter into warmth, into movement, into time. Even the largest among them, the giants whose breath reaches past planets and whose hearts burn with 1,000 suns' intensity, they too must eventually fade. But their fading is not an absence. It is a kind of giving, a scattering of the very ingredients that shape everything we know. Somewhere out there, in the deep arms of the galaxy, another red giant breathes softly into the void. Its outer layers drift gently outward. Its core tightens in silence. Its light, though ancient, still crosses space at the speed of thought, reaching worlds it will never see. That light touches dust, oceans, eyes. And then it continues, unchanged, across the centuries. Tonight, we followed one such star, impossibly vast, nearing the end of its luminous life. We wandered through its atmosphere, measured its heartbeat, and watched as gravity pulled it inward. We listened for neutrinos, felt the edges of collapse, and glimpsed the ghost of a remnant shining softly at the center of a fading cloud. And beyond all of that, we saw how, even in dying, a star gives. It gives light and heat and memory. It gives gold and oxygen and stories waiting to be told again. In this vast turning universe, everything we know has passed through starlight. The dust beneath us, the air within us, the slow rhythms of thought and dream, all shaped in part by stars that lived and burned and fell long before we were born. Their endings are written into our beginnings. Their quiet unraveling becomes the architecture of everything new. And so, as your thoughts drift slowly now, let them wander with the starlight. Let them trace the curve of a red giant's edge, or follow a filament of nebula curling through deep space. Let them settle gently into that wide, dark stillness where time stretches and stars remember. And so, under the quiet stars, the story continues. I hope you sleep well and dream softly. Good night.